You see the headlines everywhere. A desperate Chinese government rationing a failed chip supply. You read the analyst reports and one number just leaps off the page. A 95% defect rate for SMIC's new AI chips.
95%.
95%. It's a staggering figure. It's not just failure, it's total collapse. It paints a perfect, simple picture of a strategy in ruins, a panic-driven intervention. And then you pick up a Huawei Mate 60 Pro. This phone, a massive commercial hit, running on a complex 7nm chip, and the foundry that makes it, SMIC.
The very same company?
The same company that's supposedly failing 95% of the time. Suddenly, the simple picture doesn't look so simple. That single contradiction, a factory that is simultaneously collapsing and mass-producing a flagship product, is the key. It suggests the real story, the one about deliberate industrial strategy, not panic, is being completely missed. Okay, so let's unpack this. The mission for us today in this deep dive is to really move beyond that simple narrative of collapse and panic.
Right.
We have to figure out what is really happening when a company is supposedly failing 95% of the time, yet is simultaneously churning out a globally successful 7nm flagship product?
Yeah.
That gap, that vast gulf between the media narrative and the physical reality, that's where the true story of strategic resilience lies.
And what's so fascinating here is that the conventional wisdom, it almost always focuses on what is missing.
The EUV machine.
Exactly. The lack of advanced extreme ultraviolet or EUV lithography equipment. It focuses on that instead of what has been successfully achieved under these, incredibly intense geopolitical constraints.
So to understand the true state of play, we have to follow the evidence.
The empirical evidence.
Yeah.
We have to look at physical teardowns, at proven market adoption, not just, speculative analyst models that might be based on incomplete or outdated information.
Here's where it gets really, really interesting. We are constantly told that sanctions have crippled manufacturing capability at the 14nm level and beyond. That's the line.
That's the line.
Yet we have these analyst reports claiming total non-viability right next to a massive commercial success story, the Mate 60 Pro. So what does the physical evidence actually tell us? I think we have to start with the phone itself because it's the most concrete, just irrefutable piece of proof on the table.
Absolutely. The launch of the Mate 60 Pro back in 2023 was a huge technical signal to the world. It wasn't just a rumor. It's empirical proof sitting in the hands of millions and millions of consumers.
And it was torn down pretty quickly.
Oh, immediately.
Wow.
Tech Insights, which is a really respected third-party analysis firm, they got their hands on the phone, took it apart, and they confirmed that the heart of the device, the Kirin 9000's processor, was fabricated using SMICs, and this is the key part, second-generation 7nm process.
Right, the N+2 process.
The N+2 process. And this kind of technical analysis, it's not speculation based on trade data or rumors, it's confirmation. It's based on deep physical reverse engineering of the silicon die itself.
And that one confirmation, it just single-handedly shattered the prevailing narrative that sanctions had successfully frozen Chinese technology at 14nm. It demonstrated a clear technical breakthrough achieved, seemingly in direct contravention of controls designed to do exactly that.
Precisely. And now we have to address the most common misconception, which is this idea that 7nm is impossible without the very best, most advanced tools.
The ASML machines from the Netherlands.
Yes. The media narrative is that you absolutely must have extreme ultraviolet or UV lithography to achieve these advanced 7nm nodes.
Which is just factually incorrect. I mean, we know from the history of the industry that both TSMC and Intel, they both fabricated functional 7nm products without relying on EUV in their initial process development. Yeah. It's the preferred method now for sure, but it's not the only way to get there.
Correct. And that's exactly the path SMIC took. They achieved this 7nm node by utilizing existing 193nm immersion deep UV DUV lithography, so older equipment.
The tools they already had access to.
The tools that were available to them combined with an incredibly complex technique known as multiple patterning lithography. This is the crucial distinction. They are using older, less restricted equipment, but they're applying incredibly advanced, difficult fabrication techniques to reach modern nodes.
That sounds like a brilliant, if brutally difficult, workaround. Can you walk us through the mechanics of that? I mean, why is using DUV for 7nm so much harder than using EUV? What's the technical pain point of this multiple patterning?
Well, to put it simply, think of lithography as shining a very, very precise light through a stencil or a mask to print circuits onto silicon.
Okay.
For a 7nm chip, those circuits are incredibly fine. I mean, unimaginably small. EUV uses a much, much shorter wavelength of light, which allows it to print those fine details in a single clean pass. It's like using an ultra-fine tip pen.
And DUV?
EUV has a longer wavelength. The light is physically just not sharp enough to resolve the fine features necessary for 7mm circuitry in one go. It's like trying to draw that same intricate pattern with a thick marker.
So you can't do it in one pass?
You can't.
Yeah.
So instead of one pass, you have to use a technique like self-aligned double patterning, SADP, or even self-aligned quadruple patterning, which is SAQP.
Quadruple?
Yes. You might take one layer of the circuit design and break it down into 4 separate masks, printing them sequentially, one after the other, on top of each other. And for the most complex, most critical layers of a 7mm chip, there's evidence SMIC engineers might even be using octuple patterning.
8 steps for one single layer.
8 perfectly aligned lithography steps. That's 8 times the opportunity for a defect to occur on just one layer of a chip that has dozens of layers.
That sounds like an absolute nightmare for yield. I mean, the chances of something going wrong must just skyrocket.
It is. It's an engineer's nightmare. Each additional patterning step introduces immense cost and, more importantly, risk. First, alignment becomes exponentially more difficult.
I can imagine.
If the first mask is off by a tiny, tiny fraction of a nanometer, the 8th layer will be completely misaligned, and the entire chip, the die, is a defect. It's useless.
You lose the whole thing.
You lose the whole thing. Second, the cycle time just explodes. Instead of manufacturing a wafer in a few weeks, the cycle time for that wafer stretches to many weeks or even months because of the sheer number of process steps involved.
And that translates directly to what? Lower output and higher cost.
Directly to reduced throughput and a massive, massive increase in the manufacturing cost per functional die.
So the restriction on ASML's EUV equipment, it didn't actually halt progress. It just forced them into a much more difficult, much more roundabout, and frankly, commercially inefficient way of achieving the same goal.
That's the perfect way to put it.
So the key takeaway for you listening is that this 7mm chip, well, it isn't cost competitive on the global market against something from TSMC, but it exists. And it functions, and is being produced at scale.
Precisely. The ability to support a flagship consumer product at sustained high volume, millions of units, it proves an immense technological commitment and capability, even if the per-chip cost is substantially higher than what TSMC achieves with EUV. And this takes us right back to the central contradiction.
The 95% number.
That 95% defect rate.
Let's circle back to that staggering claim from that Morgan Stanley report. A 95% defect rate for Huawei's Ascend 910C AI chips, also fabricated by SECON. If the Kirin 9000's yield is commercially viable enough to sustain a massive phone launch, how could the Ascend 910C yield possibly be a 95% failure using the same foundational N+2 process technology?
This raises a really important question. It's highly improbable that this number reflects the state of a production line that is successfully supporting a complex 7mm mobile system on chip.
Right.
And so
what's the explanation?
we need to consider the typical semiconductor yield curve. When a foundry transitions to a complex new node, initial yields are notoriously low.
How low?
Often in the single digits. It's totally normal. But then they climb, sometimes rapidly, through optimization over months or even years. It's a process called yield ramp.
So that 95% defect rate, you're saying it might have been an accurate snapshot, but a snapshot of the initial experimental phase of the production line when they were just starting out.
That is the most logical explanation, yes. Furthermore, we have to distinguish between the Kirin South and the Ascend AI chip. They're not the same beast.
Okay.
The Kirin 9000s is complex, for sure, but the Ascend 910C is likely much, much larger in terms of die size, and it incorporates specialized high-density components and complex memory interfaces necessary for AI workloads, like potentially incorporating HBM or high-bandwidth memory integration.
And a bigger chip is harder to make successfully.
It's just statistics. Larger die sizes inherently have lower initial yields because there is a greater probability of a single random killer defect landing somewhere on a critical transistor.
So in essence, the 95% failure figure was likely true, or close to true, when they first tried to run that specific massive, difficult AI chip on the brand new N+2 line.
Right.
But it certainly doesn't reflect the current capacity proven by the millions of Kirin SoCs that are now in circulation. It was a snapshot of a failure that was subsequently engineered past.
Correct. The Ascend yield is almost certainly still lower than the Kirin yield today, but it is definitely not 5%. The ability to support the Mate 60 Pro at volume proves that SMIC's capabilities are far more robust and resilient than those speculative early failure reports would suggest.
And this leads us to the industrial motivation, which is, I think, the most important piece of this puzzle. We've established that using DUV for 7mm is commercially punishing. The cost, the cycle time, it's brutal. But this is where the socialist market economy framework, as it's called, changes the entire logic.
It changes the entire calculation. Exactly. If China requires these advanced chips for national security and for strategic technological competition, and President Xi has made it abundantly clear that they do, then the government can entirely ignore typical profit motives and cost penalties to crank up production.
The goal isn't profit.
The goal is self-sufficiency and national security, not return on investment for shareholders.
So they can essentially subsidize production heavily enough to crank up the volume, even if the per-chip cost or the yield penalty makes absolutely no commercial sense by Western shareholder standards.
That's it.
They are prioritizing technological sovereignty over financial efficiency in this specific strategic area.
Think of it like a wartime necessity or a national space program. You build the rocket regardless of the cost per pound of payload because the strategic value of achieving the mission of getting to the moon, it outweighs the immediate expense.
Right.
This strategic motivation completely bypasses standard commercial logic, and that is precisely why external analysts who are modeling SMIC based purely on commercial profitability metrics often misjudge their actual capacity and their output potential.
So, if the manufacturing breakthrough is real, and it proves capacity exists despite the sanctions, what about the policy that's driving all of this? We hear about government intervention and rationing, but if you look at the long-term goals and the massive financial backing, this looks less like panic and much more like a massive, focused, and deliberate pivot toward industrial sovereignty.
That's the necessary reframing. You have to look at it that way. The core driver here is not desperation. It's the sheer weight of the intensifying geopolitical conflict. The U.S. the export controls, the entity list targeting key companies like Huawei, SMIC, and JHICC, and of course the EUV equipment restrictions. All of this necessitates a firm, focused national response.
A response aimed at self-reliance.
At achieving self-reliance, yes, because the alternative is to remain vulnerable.
And this isn't just a business problem for these individual companies. You're saying it's a national mandate.
It's been elevated to that level. President Xi Jinping articulated this very clearly, stating, "Only by mastering crucial core technologies with our own hands can we fundamentally safeguard our national economic security, national defense security, and security in other areas."
So that quote, it elevates the semiconductor industry from just another high-tech sector to something more.
To a strategic, basic, and leading industry that directly supports national security and socioeconomic stability. It's foundational.
And this political imperative, it then translates directly into what we see as strategic industrial policy in action. So when the government appears to intervene, what they're actually doing is prioritizing supply for specific national champions.
Exactly. Prioritizing a company like Huawei, which has proven world-class design capabilities through its Silicon division and the Ascend series, is an incredibly logical move from a state perspective. It ensures that the domestic R&D effort has a guaranteed customer. It creates a protected market, which in turn accelerates the creation of a viable domestic anchor for the whole ecosystem and forces the entire industry to pivot away from its reliance on foreign tech.
And these interventions are operating within these larger macro strategies, right? Like Made in China 2025 and the dual circulation framework?
Yes, those provide the long-term vision. But this urgency, this acceleration we're seeing now, it came from a very clear and painful deficit, didn't it?
It did. The urgency is really understandable when you look at the self-sufficiency gap that existed before the major sanctions really hit hard.
Right.
Despite very rapid semiconductor sales growth, an average of about 20.2% increase between 2015 and 2019, China's IC self-sufficiency rate was still only around 30% in 2019. That's according to State Council data.
And the goal was much higher.
The goal was 40% for 2020, so they were falling short. And that 70% reliance on foreign chips, particularly for the high-end nodes, well, that fuels the current accelerated pivot.
Now, we also have to be fair and acknowledge the policy's growing pains. In the past, this massive investment drive, it resulted in some significant policy distortions, some very high-profile failures, and considerable waste.
We all saw the spectacular default of Tsinghua Unigroup, for example, after it had received massive state policy support.
Right. There was an era of, let's call it over-enthusiasm, that resulted in huge overlapping investments across the country.
We have numbers on that?
We do. As of August 2019, if we look just at the plants that were focusing on 12-inch wafers, which are the modern standard, there were 18 in operation, 15 under construction, and another 23 awaiting construction. This proliferation was leading to wasted resources, talent shortages, and in some cases, localized corruption scandals.
So that kind of scattershot, inefficient approach had to be addressed.
It had to be. And the government's response has been to refine and coordinate the policy through the National Development and Reform Commission, the NDRC.
Okay, so how does this new coordinated approach actually work in practice? It sounds like they're trying to apply a filter to this investment frenzy.
That is precisely what they're doing. The NDRC announced a pretty sweeping policy review that focuses specifically on preventing those overlapping investments and ensuring more targeted support.
And what are the key elements?
Well, a few key things. First is enhancing deployment based on regional agglomeration.
Meaning what?
Meaning building clusters of expertise and supply chains that are centered around already established hubs like Shanghai, Beijing, or Shenzhen, instead of just building a fab anywhere a local government wants one.
So concentrate the resources.
Concentrate the resources and the talent. They are also building a more robust risk prevention mechanism. This involves improving communication and coordination with financial institutions like banks and investment funds for early warning and, problem sorting.
So the state recognizes that a massive financial push will inevitably lead to some commercial failures.
Of course.
But they want to manage those risks proactively to avoid another Tsinghua-level default that really shakes investor confidence in the whole project.
Exactly. It's a shift from just throwing money at projects all over the map to a much more strategically managed, centralized approach that's focused on regional specialization and mitigating risk.
And what about the financial backing itself? Is it still just coming from these big sovereign wealth funds, or has the funding strategy also matured?
The funding strategy is diversifying significantly, and that signals a real institutional maturity. While the sovereign funds, the so-called big fund, are still operating, there's a strong shift now toward encouraging private capital and venture funding.
How are they doing that?
They're developing mechanisms for compensation of lending risk by local governments, which makes banks more willing to lend to these high-risk but strategically vital semiconductor startups. And they're promoting listings on the Science and Technology Innovation Board, the STAR market, which was specifically designed for these kinds of tech firms.
So that actively encourages private money into the semiconductor industry. It uses guidance and, environmental improvements rather than just direct government handouts.
And the results really speak for themselves. Equity investment in the semiconductor industry hit 140 billion yuan in 2020 alone.
Wow.
And that represented about a 4.5-fold year-on-year increase. That staggering jump in private investment, it reflects a real market confidence in the long-term strategic push.
And I recall that the National IC Industry Investment Fund, the big fund, it also strategically changed its focus in its second stage, which was established in 2019. This is perhaps the most telling sign of the long-term resilience strategy.
It is pivotal. It's absolutely one of the most important shifts. In the first stage of the big fund, the focus was overwhelmingly on supporting major production efforts.
Building the fabs themselves.
Building the fabs. Now, the second stage is diversifying its investments to focus heavily on the upstream elements of the supply chain, production equipment and materials.
Which is a direct response to U.S. sanctions limiting access to that essential gear.
A direct and necessary response.
So we're talking about targeting domestic substitution for the most constrained parts of the entire supply chain. What specific equipment categories are they now prioritizing and pouring all this money into?
They're targeting everything necessary for a full domestic production loop. This includes really specialized machinery for processes like etching, deposition, metrology, and inspection.
Can you give an example?
Sure. Etching machines, which are used to carve the circuit patterns into the silicon wafer, are highly controlled technology. Funding is now being aggressively directed toward domestic Chinese companies like AMC to rapidly mature their offerings so they can replace foreign suppliers like Lam Research or Applied Materials.
And it's not just the machines.
No, it's also the materials. Critical materials like high-purity chemicals, specialized gases, and the silicon wafers themselves are being supported to reduce reliance on Japanese, Korean, or European suppliers.
So they're not just trying to build chips anymore. They're trying to industrialize the entire supply chain that feeds those fabs, reducing their vulnerability at every single layer. This highlights the sheer scale of this strategic ambition here. We're talking about a reported $1.5 trillion industrial push, aimed at creating an ecosystem that is, in theory, structurally immune to external pressure.
And if we connect all this to the bigger picture, well, the hardware progress is clear. The 7-millimeter reality is established. But the true measure of technological sovereignty in this decade is success in the new frontier, artificial intelligence.
Right.
AI is the most demanding computational workload today. So the real question is, how do Huawei's Ascend chips actually stack up against NVIDIA's dominant H100 in this critical race?
And this is where we see the constraints really bite, but also where we see the real ingenuity in engineering the workarounds. Let's look at the manufacturing contrast first, just the raw specs.
Okay.
The NVIDIA H100, the global benchmark, is built on TSMC's bleeding-edge 4N process, which is a 4-meter class node. It houses a staggering 80 billion transistors with an estimated yield somewhere around 90%. I mean, this is the definition of commercial cutting-edge scale.
And you contrast that with Huawei's Ascend 910D or the 910C. They're built on SMIC's 7-millimeter N+2 process, which is constrained by DUV lithography. The 910C, for instance, integrates about 53 billion transistors.
So a significant gap in density right there.
A huge gap. And the process maturity difference means the estimated yield rate for the 910D is probably around 40 to 50%, which is significantly lower than the H100's near-perfect yield. And this also means the 910D's performance per watt trails by about 20 to 25% just due to the node limitations and that multi-patterning complexity we talked about.
So based on the raw compute figures, there is a clear, unavoidable hardware gap because of the lack of EUV. We see the H100 delivering about 2.8 times higher FP16 performance and 2.6 times higher BF16 performance than the 910D. That's a massive gap in raw training power.
It is. It's a huge gap. But Huawei is being highly pragmatic about this. They are compensating for the node limitations and the raw compute gap by employing a highly advanced manufacturing workaround. 3D chiplet integration. They combine multiple smaller dies within a single high-density package. This strategy boosts the inter-chip communication speed, which is absolutely critical for large-scale AI training and inference.
So by combining these multiple smaller units, these chiplets, they are compensating for not being able to cram everything onto a single, perfectly optimized bleeding-edge die like NVIDIA can.
Exactly. And this allows them to achieve very competitive INT8 throughput, which is especially vital for inference tasks, the actual deployment of AI models once they've already been trained.
And what about for training, which is the really hard part?
Well, while the H100 is still the undisputed global benchmark for massive cutting-edge training runs, the Ascend 910D enables approximately 60% of the H100's training performance at the system level.
60%.
60%. And for the vast majority of domestic AI needs in China, from running localized large language models to powering industrial automation, that 60% performance level is deemed highly sufficient and, more importantly, strategically acceptable.
And the market positioning reflects this pragmatic approach, right? The price is a big factor.
A huge factor. The Ascend 910D is priced at around $15,000, which is roughly half the H100's typical street price of $30,000. So if you are a Chinese tech firm, you're facing export controls that prohibit you from buying the best US chips. And suddenly, a viable, domestically supported chip at half the cost becomes an incredibly attractive and reliable alternative.
And the domestic market has responded.
Oh, absolutely. Major Chinese tech giants, including Baidu, Tencent, and Alibaba, they've all placed substantial orders for Ascend 910B chips, which demonstrates clear market confidence and a major shift toward local supply chains.
I think Baidu even confirmed their order publicly.
It did. Baidu, for example, publicly confirmed ordering 1,600 of these chips specifically designated for 200 of their servers. They are actively betting their long-term AI strategy on this local ecosystem.
Which brings us to what is probably the most crucial and most difficult part of this whole equation, the software stack. Hardware is one thing, but running massive AI models requires an ecosystem that took decades to build. We're talking about NVIDIA's CUDA.
The Great Moat.
The Great Moat. It supports 90% of AI frameworks globally, and it's the universal language of AI development. The challenge for Chinese firms isn't just closing the hardware gap, it's overcoming the deep integration and decades of maturity of the CUDA ecosystem.
Indeed. It's the equivalent of trying to launch a rival operating system against Microsoft Windows back in the 1990s. The entire global AI community is trained on and accustomed to CUDA.
So what's Huawei's answer?
Huawei's direct counterpart is its CANN, which stands for Compute Architecture for Neural Network Software Stack and the supporting MindSpore ecosystem. This is a massive, multi-year, multi-billion-dollar investment to create a full software parallel to CUDA.
And do we have hard data showing its viability in terms of performance?
We do. Researchers from DeepSeek, a Chinese AI firm, demonstrated that the Ascend 910C reached approximately 60% of the H100's inference performance when it was executing tasks based on their own DeepSeek model.
So that 60% number again, it's a recurring theme.
It is, and hitting that 60% mark is a huge milestone. It proves that it's capable of handling high-level AI workloads effectively.
And what's equally important, I think, is the integration success for the programmer, for the developer.
That's the key to adoption. DeepSeek natively supports Ascend processors now and maintains its own PyTorch repository. This enables seamless conversion from CUD code to CANN, and it's sometimes claimed that this can be achieved with just a single line of code change.
That's a big claim.
It is, and it's a critical one because it dramatically lowers the barrier to entry for developers who are trying to migrate their models off of the dominant U.S. platform.
But despite that progress, the software gap is still present, and it probably presents the largest long-term constraint. Where exactly is MindSpore and CANN lagging compared to CUD's maturity?
The gap is less about raw functionality now and more about stability and ecosystem tooling. While Huawei claims MindSpore can translate CUD code via tools like Musify, developer adoption lags, and certain critical high-end areas, chief among these are stability and long-cycle training. When you're training a massive foundation model for weeks on end, even a tiny bug can crash the entire operation, and you lose all that progress.
A multi-million-dollar failure.
Exactly. And the other area is the quality of the debugging and profiling tools. CEDA has decades of refinement. Its tools are simply better at helping developers find bottlenecks and errors than the tools currently available in the rapidly evolving CANN stack.
That instability is absolutely critical for the next generation of multi-billion parameter foundation models. But some Chinese firms, recognizing this higher-level software immaturity, are finding some incredibly innovative ways to get around it entirely.
This is a fascinating technical detail, and I think a great illustration of Chinese engineering ingenuity under pressure. Instead of relying solely on the higher-level CANN programming framework, some Chinese firms, including those working on models like DeepSeek, have been going directly to the lower-level hardware instruction language.
The language known as PTX.
PTX, or Parallel Thread Execution.
Can you explain PTX in simpler terms for us? Why would you go closer to the metal, so to speak, if it's so much harder to code?
Well, think of the difference between writing a document in a word processor like Microsoft Word versus writing the actual binary code that tells the computer how to render each letter on the screen.
Okay, a huge difference in abstraction.
A huge difference. CEDA and CANN are the word level. They're high level, relatively easy to use, but you lose some control over the precise execution. PTX is the low-level instruction set for the GPU itself. By coding directly in PTX, engineers can achieve fine-grained optimization.
What kind of optimization?
Things like highly specific register allocation, memory adjustments, and thread management. There's essentially sacrificing ease of use and long-term maintainability to extract the absolute maximum performance today from the Ascend hardware.
And in doing so, they're bypassing the current gaps in the higher-level software stack.
Exactly. It demonstrates a strategy of deep customization and intense localized effort to achieve parity with rivals, even if the tools they are forced to use are much, much more complex.
So we've spent this deep dive moving past the media panic and the scary-looking numbers. We've seen that the catastrophic 95% failure narrative is directly contradicted by a thriving 7mm consumer market, which has been proven by physical teardowns and a mastery of DUV technology. We've established that government intervention is not panicked rationing, but a strategic industrial policy that is meticulously coordinating investment and is backed by diversifying funds focusing on the entire domestic supply chain from the equipment to the materials.
Right.
And we have concrete evidence that a viable AI alternative ecosystem, led by Huawei's Ascend and CANN, is being actively adopted by major Chinese tech firms and is rapidly closing that performance gap despite the massive challenge presented by CDA's dominance.
And what's so fascinating here is the massive and I think largely unintended consequence of the export controls. Rather than stopping China's technological ascent, the constraints have become the most powerful catalyst for an irreversible self-reliance.
They forced the issue.
They forced the issue. The challenges they now face. The yield bottlenecks from multi-patterning, the softer ecosystem maturity gaps, and the 2 to 3 year lag in process technology. These are the natural, painful growing pains of an accelerated pivot. They are not signs of impending collapse.
Right.
The long-term trajectory, which is backed by a $1.5 trillion industrial push and a state apparatus that is willing to ignore commercial inefficiencies for strategic gain, it points towards sustained and localized growth in these strategic sectors.
The ultimate test of this self-reliance strategy won't be measured in today's chip yields, but in whether China can close the 2-3 year gap in process technology and software maturity before the next generation of global accelerators widen the divide beyond reach.